the basic thing that it does. Okay, so um, I'll bring up my screen, and then we would do a few whiteboarding to explain how linked list works, and then maybe on Friday we could try to write some code to work with it. Hopefully that's fine with you guys. All right. So I hope the screen is up now. Um, you can see the screen, right? Just to
Yes,
confirm.
yes, yes, Max.
Yes.
Yeah, great. So,
But you can zoom in
uh,
a little bit.
yeah, sure. I would actually use this like after we've talked about it a little bit. This is a different method where we would use to work with it. But for today, let's start on a clean sheet. Right. So um, we've seen or we've worked with arrays, and we know that arrays are contiguous data types, or they have a contiguous memory block allocated to them. Right. So maybe we might be asking why we would need a linked list when we have a data structure that is able to already keep information when we need it. Right. The issue with an array is that, let's say, we already know that, let's say, if you're trying to work with an array, oops, if we need to work with an array, we probably have to say something like, let's say, if it's an integer, we say int numbers, then we would have to give it some size. Okay, so this size over here that we've given it, in case we don't use up to this size, we've wasted that much memory that wasn't used, or if we have to use more than that, then we have to come back and increase the size of the array, which is also a limitation because right after we declare or we define an array size, it cannot be changed. Okay, so that's also one other limitation that we have. Then there's also the possibility of using dynamic arrays, whereby we are going to use the heap section of memory to allocate memory. It still has the same limitation that we can, although use malloc to assign memory to to the array and reallocate it to get a bigger size. And that's an expensive operation because every time we need to increase the size of the array, we would have to copy everything that is or everything that was present in the previous one to this new array, which is not a very effective operation. So the reason why we need the linked list is for such cases. Let's say if you're going to be doing lots of insertions, okay, and we also don't want to be bound by the case where uh, like we would have a lot of memory blocked for not using them, or we will have not enough, and then needing to copy over and over again. Right. So for this reason, we bring in this data structure we call the linked list, which is essentially something that looks like this. We essentially have some kind of data that is scattered across in the memory, and the only thing that they know about themselves is that, well, after me you will see this one, or after me you will see this. So it is not contiguous like the way that we saw arrays to be, where the data is in straight line, or it's in a compact side by side thing. So um, with the linked list here, as I'm saying, that it is basically a data structure whose only idea that it has is that, okay, well, after me this guy is next. So the only thing that it uses is that it's able to point or have a pointer to the next person that it needs to reach for the next data. So it's something just like this. Let's say from here I go to this side, I probably might would come here, and it is not mandated that I would have to go through this before I come to here. I could go all the way to this side and probably even come here before I come here. Okay. So see that with this, we are not really bounded by the fact that the thing has to be in contiguous form. It could be in any way at all. Okay. So this is just to show the fact that the this linked list that we were talking about, it doesn't have to be in a contiguous form. You can start from one side, go all the way to another place, right? We understand that if we are dealing with an array of integers, and let's say our starting point is 100, we expect that the next array that we are going to deal with must have the address of 104. And that's because an integer has 4 bytes by default on 64-bit machines. So um, for an array, we know that, okay, well, if I'm on index 0 and the starting address is 100, the next one should be 104. The next should also be um, 4 more than the one I'm looking at. Right? But for the case of a linked list, it can be so different. Right? We can have it like this. We can say maybe this one over here, like the first address, the the first thing we have here, which we call nodes, is, let's say, 100. The next one here could have been somewhere, let's say, around 600 and 760. I'm just using these numbers randomly, just for the sake of exaggerating it as much as possible. And this one here could be somewhere, let's say, um, 930. It's somewhere, let's say, 1034. Right. Hopefully you are getting an idea. So the whole thing is that the data is not in contiguous form as we expect it. It is scattered across memory, and the only way that they know how to connect to themselves is through these pointers, or let's say through these arrows. That, okay, well, from here I know that I will have to get to this point to get the next thing. Then this guy also knows that, okay, well, here I am. If I need to get to somewhere else, I would have to go to the next person to ask them. All right, so it's basically like a chain of um, data that we have, where we have to move from one side to the next person before we can be able to get the data that they are also holding. So we have to move in a linear fashion to get the data that we are looking for. Okay, so I'll just populate this data with some, like, the rest of the addresses. This is 990. Then this over here happens to be, um, let's say 1010. Okay, so the addresses could be very big, but I'm keeping it to this way. So this kind of data type here is just allowing us to allocate memory when we need it, and only when we need it. Right? So for the first time when we needed this kind of node, right, we only allocated memory for this node. So we don't allocate memory ahead of time. Okay, and we also don't have to resize the uh, we don't have to resize to accommodate for new things. If we need something, we just have to do, like, we can just allocate memory and insert it just like that. So the reason why we may choose an array, so a linked list over an array, is, let's say, when we do lots of insertion and deletions. Okay, so for instance, though the you can say that the cost of insertion into an array is O of n, which I hope we understand. Right? Normally, if we have to insert into an array, we have to be sure that after we are done, we have to shift everything to be able to get to the place that it has to be. But then, if we need to insert into a linked list, we can just say something like this. Let's say uh, between this this node and this node, I would like to put something in between them. I don't have to worry about shifting everything. All I need to do is to just, first of all, have what I need to insert there. So something like this. That's what I need to insert there. Now, all that I have to do is just say, okay, well, now this person, oops, sorry, this person here is now going to point to this, and this is going to point to that. So it's all a matter of just moving the pointers around. So here, oops, sorry, just that. So now instead of this pointing to this, I'm just saying that okay, well, this one points to that, and this now one now points to this. Right, so there was no extra shifting that was needed. All that was needed was like we just needed the node that we needed to insert. We insert that at the position we need it to be, and then everything is just as it is. So the actual insertion in a linked list, you can say, is constant time because we don't need to shift things about before we can do that. Okay. The only thing that we can say is that well maybe if we are um, traversing, then we can count that. But the actual insertion doesn't cost much, like in the case of an array. Okay, so also when it comes to deletion, once we are done deleting, all that we do is just adjust the links. We don't have to shift things about to be able to um, remove anything from a linked list. Okay, so for some of these reasons, that is why a linked list is better than an array. Okay, so if we envision or we uh, can see that this is going to be a lot of the things that we are going to be doing, or most of the operations are going to be like this, then we will have to use a data structure that supports this much better. So some of the operations that we perform on linked lists are these: we do insertion, we do deletion, and mostly that's it. We can insert, we can delete, we can also search. We can do quite a lot of things, but I'm just mentioning the basic ones. We search, we delete, and then we can also traverse to search for something within it, right? But then if we want something that we will be searching through often, a linked list wouldn't be a better option because there's that cost of us having to move from one side all the way to the position that we are looking for to find it. There are other better data structures that can do this much better. But if you realize that we are going to be doing lots of insertion and deletions, and we don't want to have extra cost of shifting things around, and we also don't want to be bound by the issue of allocating memory and reallocating memory in a way that would limit us in terms of memory, a linked list is going to be much better. Well, also sometimes you see with an array, we need a contiguous form of memory to be able to do that. And sometimes we don't have that much contiguous space available for us to use. So it wouldn't work. When we are trying to maybe malloc it, we are going to receive an error. But then because a linked list node is only created when it is needed and we free them immediately after they are not used, we still have the ability to just put them anywhere in memory. And remember, that's our other advantage. They are not contiguous, they are scattered across the memory. So, as an array might need a contiguous space, the linked list wouldn't need that. So it can still fit somewhere within memory before maybe if later everything gets filled up, that's fine. But then it has the advantage of not failing immediately when we need some amount of space, unlike an array. Because if we need, let's say, 40 bytes for an array at a time, a linked list might take less than that for one node, and we'll be fine, right? And also, in the case of an array, if we delete something, we may leave that um, memory still hanging around in memory, and we'll be wasting it. Okay, so if we are certain about some of these things, then we can say that, well, though an array is able to do kind of these things, I'd rather go for a linked list because it will be able to handle these things much better than its counterparts, which is the array. Okay. So if you realize that most of the things that you need wouldn't require like um, data or let's say memory allocated upfront, then we are probably looking at using linked lists. Or if you find that you'll be doing insertion and deletions in a way that um, wouldn't need like extra memory, let's say um, like the same thing, memory allocated ahead of time, then a linked list is also going to be better. Okay. And there are other usages that we would come to as we go along, right? But I like to let's say pause for a while and then see if we have any questions so far. Anyone with a question?
Uh, Maybe I can say something.
All right, sure, yeah, sure.
You've talked about maybe one thing uh, that I'm taking away is there's ease of insertion. Then the other thing you've talked about is efficient memory allocation. And
Yeah.
compared to arrays, maybe can you maybe mention some things that will make you to prefer arrays to linked list?
All right, sure. Yeah. So you remember that I was saying that let's say if you be searching the lists often, then a linked list wouldn't be a best option. Right. All right, because let's say for an array, if you want to find something, let's say we know that we are trying to grab that something at a particular index, it's going to be in constant time. So if you're going to be doing most of those operations where we are going to be grabbing data at particular indexes, right? An array is going to be a much better option because right after we give it the index, we get what we need right from the in constant time. And then with a linked list, you would have to traverse from the beginning all the way to wherever that data is stored before we can get it. Okay. So in the worst case, that means we have to go all the way to the end of the list to get it. Right. Also, let's say that if you maybe need something very simple for like what you're about to do, let's say you know ahead of time that you just need this much memory for everything that you need to do, and you don't need anything much more than that. I think a linked list, sorry, an array is a much easier method to use. Right? So um, yeah, like we could say that if you need to be searching the like the array or the data that you want often using some indexes, then an array is a much better counterpart or a much better option than the linked list. But there are others as well that we could explore.
Thank you, thank you.
I see Ahmed has his hand raised.
Yeah, 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 yeah. Can you guys hear me?
Yes.
Yeah, yeah. So I'm sorry about that. So I have some internet problems, but then for the meantime, okay. I've heard you. You were saying one advantage of linked list is that to array the items don't have to be in a contiguous form. What did you mean by that?
Okay. So with it not being contiguous,
Yeah,
right?
yeah. That's it. So maybe can you try explaining that to me? I think I don't get it.
All right. Sure. No problem. Okay, so in normal terms, you see that let's say we have something like this, right? So in the terms of an array, we can have something like this. Let's say these are the boxes in memory. Okay, so I have something like this. So this is just my way of representing the memory, right? Just something small like this.
Okay.
So here I have one, two, three, four, five, six, seven, 8 slots for my memory. Okay. So in the case where we need to allocate memory for an array, okay, because it is indexed or based on the implementation of an array, we have to take the memory side by side. So let's say that okay, well we are trying to say that we have an integer uh, array, let's say of four numbers. If we say something like this, right, what happens is that the computer would go ahead and then block out the one, two, three, 4 bytes over here, or place the one, two, three, four, right? It will take the first four. Um, Let me try to make it a different color, right? Something clear. So, um, when we say something like this, right? The data that we are, or the storage that we are going to be given or be allocated is going to be um, side by side. So if we are given the first 4 bytes, that's how it's probably going to look like in memory. So the concept of it being contiguous is that the data that we are given for the array is side by side in the sense that from one place we can go to the next and we can even um, what's the word? Uh, Words fail me something. So we can anticipate what the next is, right? So um, you understand that an integer is 4 bytes, or it takes 4 bytes by default. So for the sake of argument, let me say that each one of this place is 4 bytes, just so that I can uh, like use that as an example. Let's assume that each one of these over here is divided or is subdivided into four, right? So here is going to be 100, and then here is going to be 104, here 108, and in that order, right? So essentially, what I'm trying to say is that if here is subdivided into four parts, then that means we're going to have 100, 101, 102, and 103, right? And that is 4 bytes for the integer. So essentially, I'm just trying to say that the contiguous nature of the array is that we are given memory um, in a fashion that is like, let's say, linearly, right? It's given to us. I'm trying to find another word, right? It's in a side by side. I think that's a is easier way to say it, or it's um, in a counting form. Right. So from here we are going here in a fashion that we can also anticipate. Right. So if I give you an array, you can anticipate that okay, if the first index is here, and if I add this much, I can get to the next data, or the next element in the specific index. But we can't do the same thing with with a linked list. So hopefully this is maybe turning it out a little bit. I can't find the word to uh, use for this one. Yeah, but basically they are side by side in the sense that they are in counting form. Or if anyone has a different way of saying it, I think
Uh,
I'm down. But yeah, something.
yes, yes, Max. I think you're on the right track. And then You know, take for example
adjacent.
the yeah, take for example the array you've just drawn, and you have given it the memory addresses. You realize that for an array, the first element will occupy 10, 101, 100. The next one will occupy 104 if they are integers, and the third one 108, the fourth one 10. Actually, it will be if you are considering hexadecimals, it will be 10c. Yeah, that's contiguous. That is like elements are next to each other, adjacent, neighboring. But for that way, we say it's contiguous. But for the linked list, if Maxwell, you can scroll to the other side of linked list so that we can, yeah, you realize that this one can be at 100, the other one can be at 760, the other one can be at 930, the other one can be anywhere in the memory as long as in this. If you are using malloc, maybe in the heap, and then you realize that this is not adjacent to each other. Uh, think that is somewhat different from the other one, which is adjacent. So this one is not contiguous, the other one is contiguous. The other one is neighboring each other. But this one doesn't have to be in a certain way. You can place it in as long as you have the pointer that points you to where it's located. That's what I'd like to say.
Yeah, thank you. Ahmed.
Yeah, yeah. So okay, okay. I think I've got what you guys what you've said, but then okay. So a quick one. So is that an advantage or a disadvantage? Because in a way, I think if the elements are side by side, like in the array, maybe accessing them will be easier, and also maybe if you want to change the elements, it's going to be easier compared when they are not side by side. So while in linked list, is that supposed to be an advantage or disadvantage?
Okay, so this has like an answer in two folds. It's a yes and a no,
Mm-hmm.
right? So at times is an advantage, other times is a disadvantage. So earlier I was saying that in the case of a linked list, we only allocate memory only when we need it,
Okay.
and we deallocate right after we don't need it.
Okay.
So I was also mentioning that let's say if we need an array of let's say 40 elements
Okay.
at a time,
Okay.
and because an array is contiguous, if we don't have that much memory in contiguous form at that point, we wouldn't be able to allocate memory for that array. Okay, but then with the linked list, since it is scattered across memory, like in the memory, and we only allocate one at a time, we'll be able to allocate memory
Am I the only one who can't hear him?
Yeah. Also, I thought it was my internet actually. Yeah. I also can't hear him. I think you are stuck. Hey Maxwell.
Mm, I think his internet.
Yeah.
Yeah. Uh, Maybe just to iterate what I was trying to say, I think it's a yes and no answer for that. And you remember when he was talking about the advantages of like when do you prefer an array to linked list? Max said that most of the time when you have the index of the elements, and since they are contiguous, it can be easier for you to keep iterating through them and accessing each one with ease, rather than the other one for linked list, where every time you have to go from the first to the second to the third. Like you need to go because the first element will show you where the second element is there, and
Okay.
the second will show you where the third element it is. So that way you'll be tedious in terms of like maybe time complexity. It will be taking a lot of time. But in array, if you know the index, you just go direct to where it is located, the location of the element in the array. So at that point, having a contiguous memory in array, it's a good thing. And for now is okay for me. This one is like, let's say you have an array and then it's contiguous, but the memory size is coming to an end. So realize maybe an overflow can happen, or part of your let's say part of your data in the string will be chopped off. So, but for the linked list, you realize if you can store and you realize there is no memory on that side, you can be allocated to the other side of the memory, even in the middle, anywhere, as long as memory is available. But for an array, when it's contiguous, they have to stick together. So that's what I'd like to say. But yeah, I think he's back. We'll keep on that idea.
Yeah.
Yeah, thanks, Samson. Thanks. Thank you. Um, Ahmed, are you okay now? I was also trying to do this, and my network also failed out. So uh, yeah, but I'm back now.
Yeah, so I think I've gotten it. So it's more like 50-50 in a way. It's an advantage,
Yeah,
in a way it's a disadvantage also. So it depends with why you
yeah,
want to use it. Yeah. Okay.
exactly.
Yeah, you can
Yeah,
continue. Thank you for that.
sure. So just as a final thing, you see, uh, just to confirm everything. So you see, currently we have eight and we've used four, right? And here I'm trying to also allocate memory for 10 elements, but then I have only one, two, three, four left. So this is going to fail, right? But then if it was a linked list node, I'll just allocate one, and then probably maybe it might just take some. Oops, it might have taken just somewhere somewhere in memory, and yeah. So that's everything that we're trying to say. So there's an advantage and a disadvantage in different contexts. Yeah.
Yeah. Okay.
Yeah. So that is really maybe what right. Yeah. So um, let's say that's like in abstract terms what we have for a linked list, and it is the basis for other data structures like the queues, the stacks, the binary trees, and like there's a lot of other data structures that depend on this, and like there are also some things that actually are used with linked lists that make them very useful, right? But then mostly, like I was saying in the beginning, if you find that most of your operations are going to be insertion and deletions, then I think your go-to would be a linked list. But if you're doing lots of indexing, as in to find where the thing is, to grab it at multiple times and very frequently, then a linked list would be a bad option, and you probably would want to use an array or a better data structure like a hash map, right? So both of them have their use cases where they are good at and where they fall short. Okay. But as we will see later in the days that we will learn about stacks and queues, we will see how um, different types of linked list or array type of stack would behave, and we would also be able to like talk more about the advantages that we are getting here and the advantages we are getting at the other side. And I think it would reinforce everything that we are talking about today, right? But um, that's really what we could talk about for now. let's say on Friday we will talk about how we are going to model the linked list and go away from like go on from that side. Someone's on is up. Yeah, man.
Okay, so okay, I know you just wanted to do a small, like an introduction on linked list, but then the session I think is going on pretty well. Can you just maybe do a small code so that next week we'll build up from there? Yeah,
Oh well.
my
So you see,
thoughts.
like
Okay.
yeah, no problem. I mean, I was trying to like be within the time so that we can uh take in as much as possible and not take too much, right?
Okay.
But well, what can happen is this here. Okay, so um, I think so. This is how we started. Since we are using the C language, so we have the structure that we are going to use for the node. Right? So we have to define the node structure for the simply linked list. So as I was saying that we have some kind of data and then it's able to point to a certain thing, right? And the way that we are able to do that is using structures in C. If it was a different language like an object-oriented programming language, you probably use classes. Okay, but then here, what we're going to use is a structure. So essentially, what I'm doing is that here I'm defining the like the data portion of uh, the single linked list as a data, and it can be multiple data though. It doesn't have to just be one. It can be multiple stuff, but just using just this one for convenience. And then the next thing that really makes this a linked list is this self-referential thing that we are able to reference another node, right? So this next point over here is going to reference another instance of the node. Um, I'm tempted to say object. Yeah. So um, since I think that makes sense to all of us over here. Right? So basically, there's going to be pointing to another instance of the struct um, data type. Okay, so that's what we will have for the node structure. Okay, and then for this particular one that we are about to do, I would like us to keep track of the head and then the tail pointers. So here, um, what we're going to do is after we've created the node structure, we would also define a linked list structure, right? So that we would use that as our means of setting up our um, linked lists. Okay, so here the advantage that I would like to point out is going to come in soon because you see for today we didn't talk about the head and then some other things. Right. So I would like us to maybe take it in that step so that we can grasp it much better. Right. So if you guys don't mind, we could like rather use this chance to accumulate what we've done so far today and try to come back with this one because this one is going to be a little bit different than the one that maybe you have done before. If you have also done this one before, then that's fine. But here, what I'm trying to do is that we are going to keep track of the head and the tail pointers, so that we can be able to cut down on the cost when we are inserting at the end of the list. Okay, and this is going to be handy when we are talking about queues, which is a different data structure. So um, for today, my goal was to talk about it in the abstract data type format. Then on Friday, we could talk more about it in the sense of it's coming into live code, right? So, Ahmed, please,
Okay.
uh, we can. hang in there for today. On Friday we can write lots of code. There's a lot of concept that I'm looking to bring in. So I think for now, if we start, it's going to be limiting, and also maybe uh, we probably might not catch that very well yet. So
Okay. Okay. Sure. Sure.
I'll
Sure.
play that we wait until Friday and then we actually hammer it well.
Okay. Okay.
Yeah.
I think it's okay. I get your point. Yeah. So I think we'll digest on this while we wait for Friday.
Yeah.
Yeah. So.
Yeah. So essentially, what I'm trying to say is that we have the node structure, then we also have a linked list structure. Right. So here we are keeping the head and then the tail. But we're also keeping the size of the linked list. So every time we insert into the linked list, we are going to keep the
Six plus one.
we are going to increment the size so that we know how many nodes are there at any particular point in time. So that every time we need the size of the list, we don't have to traverse to go and get it. It's going to be in constant time, right? As well as if we delete it, or if we delete a node, we decrement it. So it's going to be in that order. Also, there are going to be other things that we are going to keep track of. There's going to be a function that is going to basically a function pointer that is going to like point to a user-defined function, which is going to be used to, like, let's say, clean up nodes when they are removed, right? So some some few things about that, right? So that's about it for the linked list structure. This one here is just like a summary of it, but then there'll be more that'll be added. Right? And as part of that, we will have to initialize our linked list to keep track of all of these things. So we'll have an initializer function that will keep track, or sorry, would um, initialize our linked list for us so that we can start working with it. Okay, so the whole idea with this one here is that normally in the beginning, or the usual way of working with linked lists, we always keep the starting point of the linked list, and then for every time that we need to either insert or delete, we start from that beginning and then go through to find wherever we need to insert or where we need to delete, right? But at times we may find ourselves inserting at the end every time, right? And because a linked list is in a way that we always have to start from the beginning before we get to the end, right? It is, let's say, efficient that we can keep track of the other end, so that we know that okay, this is the starting point, and this is the ending point. And this part too, I find that some people who already understand double linked lists confuse it with the next and previous pointers. They are not the same thing. We will explain more of that when we go here. Basically, I'm saying that this is the starting point of the linked list and this is the end of the linked list. So if we want to remove something, or sorry, if we have to insert something at the end of the linked list, it's just a matter of referencing the tail pointer and then inserting right after that. So this way we are able to cut down the cost of traversing to the end of the list before inserting, which we will see more of that as we start to do that. So in the beginning, when the list is empty, I'm saying that we are going to set both the head and tail to the new node, right? But then when they are not empty, we are going to do something. Oops. Sorry, I think I there's some more data. Give me some time. I think I might have lost something. Uh, Give me something. I have to grab something.
Okay.
Uh, um, yes. So yeah, this is actually like the most up to date version of the thing I'm trying to show over here. So there's quite a lot of information. Also, I was saying that like it's going to be better that we talk about it uh, at a particular time. So yeah, so it would come in from the Friday, but then like the whole idea is that we are going to keep track of the starting point of the link list and then the ending point of the link list, just so that in the cases where we have to be inserting a lot of the time at the end of the list, we wouldn't be um doing lots of traversal, which is not going to be a very efficient operation. Okay, so that is, let's say, a gist for what we are going to be doing. Right. And I think I would also share a read-only version of this over here for you to look through if you are interested in. And yeah, as we wait for Friday to come. All right. So there's a lot packed, so I'll just like to take it slow and in bite sizes so that we can all take it. Very good.
Yeah. So far, so good from me. Maybe the rest.
So
Yeah.
Uh, Maybe can say something. Uh, Maybe as you prepare for Friday also, would you also spend some time and bring people up to date in terms of structures? You know, some may be finding it hard to appreciate why are we using structures in this kind of data structure.
right,
Yes, in terms of like first talking about the data, the structures. How do you define? And in terms of pointers, I can see most of the time when we are using a structure, we have a pointer, and the pointer is there that it's pointing to the name, like to the structure we are trying to create. You know, such kind of things. Uh, Try and have shed some light there. And something else, uh, maybe also as we prepare for Friday, we can also look into the time and space complexity. You know, maybe such kind of things can help us also appreciate why we prefer a certain structure, data structure, to the other.
right, sure,
Yeah.
yeah, yeah, yeah. And with regards to the structures, I shared a book in the group one time, mostly on pointers, and it goes over pointers and structures. So um, if anyone is also interested to learn more about that, they could also be looking at us data since we are all learning
Yeah.
together and then working through that. Yeah. So I think I would also bring it up more when we are building up the structures for the node and then the linked list. Yeah. So we can discuss more of that over there.
Okay. Okay.
Yeah.
Okay. Maybe you'll try resending it again because some people are not around. And thank you for the session. It was really a wonderful session. So maybe we'll build on that. And yeah, guys, I know I was supposed to present something also today, but then sorry that I didn't present it because of my internet connection. So on Friday, I think I'll start with that, and then okay, Maxwell, you'll tell me because you're our host. So Friday, you let me know when I'll present, and then you can continue with what Samson has said. Yeah. So anyone else has a comment? Okay, let me stop the recording. Okay, maybe say something to finish up, Maxwell, and then I stop the recording because the last person. want to be in the recording. Okay.
All right. So just as we talked about, we said that the linked list is a different kind of a data structure which allows us to store data in a non-contiguous format, which has some advantage over arrays in the sense that if we are doing lots of insertions and deletions, it's a much better option than a link, sorry, an array in the sense that with an array, every time we insert or we delete, we have to do an extra operation of shifting the element around. But that's not the case uh, with an array, with the linked list. Okay, so um, we said that we are going to be building a linked list in a way that we are going to keep track of both the head and the tail, make sure that when we are inserting or deleting in our linked list, we are going to be uh, performing much more efficiently. Right? So we will discuss structures or structs in C a bit more before we even go into like the creation of these things as part of doing all of this. Right. So for now, we ended on only talking about the linked list as an abstract data type, talking of what it does, how it differs from an array, and some of those other few things. And we are going to do the implementation in our next sessions. So I think that's everything for today.